Alright, welcome to the Turdferg channel here on YouTube. If you are watching this video, I'm going to assume you're either trying to finish my specific heat lab or you're trying to finish some other specific heat lab, since they are rather common. So let's see if we can get started into it. What I've got up in front of me right now is a little sample of data that you can actually see. And this is what a student of mine has done. They've got a sample of copper, and here's kind of what's happened. If you don't remember your procedures, you should have put in the inner cup of the calorimeter, and that's what this little black object is. There's my calorimeter. Calorimeter. So there's my calorimeter. Over here is my steam generator. And what I have done is I have heated up a piece of metal inside the steam generator, and I'm going to take that piece of hot metal and I'm going to put it in this water, cap it off, and then measure the increase in the temperature. So I've got cold water, hot metal, and I'm going to put the hot piece of metal into that water. Now, by looking at this person's data, wow, that didn't make a lot of sense. But anyway, by looking at this person's data, they've told me that they've got 188.8 grams of water inside here, according to their measurements, which was a lot of water. They had to really put a lot of water in there. They've told me that that piece of metal that they've got has a mass of 57.6 grams. So they've measured the mass of the metal. And then here we go. We need some temperatures. We need those two masses, but now we need the temperatures. Well, according to their data that they give me, they said that the temperature initial of that metal, right before they dump it in here, they've got 87.8 degrees Celsius. And then according to their same data, they've got that the temperature of this water, and I'm going to write TIW. I know the old lab says TiH2O, but I hate writing H2O when I could just write W in its place. They've got temperature initial of the water at 23.8 degrees. And then what's going to happen is they're going to then take that piece of metal, get this temperature, get that temperature, and then switcheroo. Put that hot piece of metal down into this water, and what should happen to the temperature of that water? The temperature should rise. Well, that's what you were supposed to write down over here. You were supposed to record those temperatures. So they've dumped it in, and according to them, their first number is 23.8. Well, I'm going to assume that's 23.8 is what it was before they dumped the metal in. So 23.8, then here we go. Temperature starts going up, 24.3. 24.7, 24.8, 24.8, and you could have tried to do it even more, although I doubt it. It looks like they tried to get a temperature about every 30 seconds. Once the temperature stays the same, it's pretty much done. Now, there should be a good question, and, well, hold on, let me finish my first thought. Dadgum, ADD is tough. One of these numbers is my temperature final. Well, it doesn't necessarily have to be the last temperature, but it just so happens on this one it is my last temperature, because the temperature got up and it stays the same. So my temperature final is going to be 24.8, even though I've got 24.9. I'm going to correct that, 24.8. There, that's going to be my temperature final. Because if the temperature stays the same or starts to fall, then I'm done. So there's your temperature final, this temperature that I got up to. Now, what about this? This would be a good question. What if my temperatures went 23.8, 24.3, 24.9, 24.7, then quit? If you were doing this lab and this happened, I would go ahead and stop. Because here's the thing, sometimes that calorimeter will cool off. That biggest number, if it starts to fall, I'm not interested in it. I want that number. That would be my temperature final if that's what my data looked like. But anyway, my data don't look like that. Mine looks like this. All right, so now I've got my temperature final, and that's going to be right here, 24.8 degrees. So I'm getting it here. So I've got my masses, I've got my temperatures, I've got my temperature final. Basically, to do this lab, what the equation's going to look like, you see, here's the thing. Heat is not created, it's not destroyed, it's energy. So my premise in this, it's a conservation of energy. And I'm just going to write this. Sum of Q equals 0. And that is a very ugly looking sigma sign. It's supposed to look like that. But anyway, the sum of my heats should all be equal to 0. Which means if I take into account the heat lost or gained by the metal, if I take into account the heat lost or gained by the water, then all that should be 0. Because in this problem, the metal gave off energy, the water absorbed energy. So the metal lost heat, the water absorbed heat. The idea is, if the metal lost 200 joules of energy, the water gained it. So in the end, your change in energy is just equal to 0. Nothing was created or destroyed. At least that's, in theory. And that's assuming your calorimeter was perfectly insulated. So here it is. Now, you might be doing this lab, and someone might have had you take the mass of the calorimeter. If so, you would just write plus Q for calorimeter equals 0 into it. But this is just a general chem lab, so that's not even in this one. So what I'm going to do is this. If you don't remember what the equation is for Q, here I'll write way down here on the bottom of my paper. Q is nothing but MC delta T. And if you don't remember what delta T is, that just means change. TF minus TI. So what I'm going to do is I'm going to write out this MC delta T for each one of these. So here you go. Beefy equation time. And you're going to use the same equation this whole lab. If you don't really remember, mass stands for mass, obviously. C stands for specific heat. That's what this lab was about, was specific heat. Again, if you don't really remember this stuff, every material has its own specific heat. So in other words, different materials gain and change temperature easier than others. If you've got a swimming pool, for instance, it takes a lot of heat to heat up that swimming pool. But you stick a piece of metal in a fire, within that long, the piece of metal's hot. Metals have a very low specific heat. Now, I do need to make sure you remember one thing for this lab. The specific heat of water is 4.186 joules per gram Celsius degree. Oh yeah, there's different units. It can be 4,000 if you're in kilograms, and it can be 1 if you're in calories. But we're going to be using this for the sake of this lab. So let's go back up here and write out the equation. This is going to be the equation we use to do the entire lab. I'm going to write an MC delta T, MC delta T, MC delta T, for each one of those two Q's. So I'm going to work it out. So this is going to be, and I'm going to use up this whole width of this page here, mass of metal, C of metal, temperature final minus temperature initial of the metal, plus. Now usually somebody's sitting here asking, why did you not write temperature final of metal? You wrote mass metal, C metal, temperature initial metal. You wrote out everything, but you did not write out temperature final metal. That's because the temperature final for the metal and the temperature final for the water are the same things. After you put that piece of hot metal in this water, the metal cools off, the water heats up, and in the end, they should all be at the same temperature. And that's where this temperature final comes from in here. So now, let's see. You should be able to write the equation for water. Ready, go. Okay, if you wrote MW, CW, TF, once again, just TF, minus TIW, then hey, you did a good job. So, there's the equation. This is my only equation. I'm going to use this to work every problem. You see, the only thing that you don't know is C for metal. You actually have all this other stuff wrote down, except for C of water. But hey, that's no big deal. We know what it is. It's 4.186. So now let's go back up here and try and plug some numbers in. So my mass of metal, according to my calculations, my metal is 57.6 grams. So now I got a feeling I'm going to use up every single inch of this paper. So 57.6 times. And now C for metal, well, that's what I'm looking for. I'm going to write it in green to kind of change it up a little. And then temperature final. See if I can find my temperature final. My temperature final was 24.8. minus temperature initial of the metal. Well, my metal was 87.8 before I made the exchange. Plus mass of water. I had 188.8 grams of water. I don't know why I wrote that G there. It was unnecessary. C for water is 4.186 joules per gram Celsius degree if you're writing out units. Temperature final is still 24.8 minus temperature initial of the water, which is 23.8. Now I'm done with this. I don't need it. Minus 23.8 degrees Celsius. Everything's equal to 0. So I do need a calculator now. Here's where most people kind of mess this up. They get carried away. You've got to subtract the difference between these two before you do any multiplying. So, like for me, whoa, what is, I've been typing my calculator. That's some cool looking stuff. Anyway, so like for me, for instance, mine would be, let's see if I can't do this, 24.8 minus, what have I got here, 87.8. So I've got negative 63. So there's my difference. So negative 63 times 57.6 times 57.6 equals negative 3629. So this is negative 3629. I'm trying to keep that little C in a different color so it stands out. C of metal. And now, what have we got here? Look at this big old thing. But notice what I'm going to do first. I could put in parentheses, but I want to make sure you do your order of operations right. Subtract the difference between those two. 24.8 minus 23.8 equals, I seriously just typed that in the calculator. What are the odds? The difference is 1. And now I'll multiply that out. 188.8 times 4.186 times, here you go, times 1. I'll throw that in there. That's amazing. And that's 790. So plus 790, and it's all equal to 0. Well, now I need to finish this. So negative 3629 Cm is equal to negative 790. Well, I love this. My negatives cancel, so plus, plus. And now let's do a little division. 790 divided by, here comes the drum roll, divided by 3629 is 0.218. Well, I do not have very good numbers here. 218, and this would be J over gram Celsius degree. So I'm going to make sure and write my unit. So C for my metal equals, and for me this one was copper. Well, that's terrible lab results, because C for copper is not 0.218. But oh well, I've done all my calculations right. Now what you should do this same calculation for your 3 metals that are left. So you should have 4 of these calculations in your lab book. 1 for copper, 1 for lead, 1 for whatever else you had. Cadmium, stainless steel. You should have 4 of these calculations. A matter of fact, specifically, looks just like this. You should have 4 sets of things that look just like that. You don't have to show me that first equation, but I want to see this. 4 times over in your lab book. All right. Now, let's say you're done with these calculations. Let's work on finishing the lab. Well, if you're going to finish the lab, you need to know these actuals. This is what your lab was supposed to look like. Now, we can see that copper is really 0.38, so I did not do so good with my 0.218 right here. So I got 0.38. Well, you can probably figure out what I need to do now. I need to do my percent errors on these calculations. So let's go back in here and do these percent errors. I guess I can just do them on this sheet of paper. You need to write them down here anyway. So there's your actuals. Pause. Write those down. Okay. Now you should be good. So let's do our percent errors. percent error is equal to E minus A over A times 100. And then what everybody always forgets, and apparently the softball team needs practice day. That's fascinating. Anyway, now what we need to do next, I want to put that E minus A in absolute value brackets there just in case you need that. And let's see what we can do number-wise. So this would be for my percent E for copper. That's what I'm about to do. Percent E for copper for me would be E. My experimental for copper is 218. So for me, 0.218 minus copper is 0.380 over 0.380, then times by 100, so I get my percent on here. Where's my calculator at one more time? And I could put all this in there at once. See if what we got here. I've got 0.218 minus 0.380 divided by 0.380. And then, woo, this is going to be terrible. Times 100. Oh no, I've got a negative percent error. Just remember, it was absolute value, so there's no negative. So I've got a 42.6% error, which means I did pretty terrible in this lab at this rate. Okay, it's really not me. I copied these out of somebody else's lab book. So here we go. This is their lab book. Blame them, not me. So I love bells. It's just part of teaching, though. But anyway, so yeah, trying to work, and I've got 300 announcements. So there's your percent error, and that's how you do it. You should have a percent error for copper. You should have a percent error for your lead. You should have a percent error calculation for, trying to think what else. Everybody had zinc, and then some of you had cadmium, and some of you had stainless steel. So you should have 4 of these calculations. All right, so what do I want you to write in your conclusion for this lab? So your conclusion for this lab. Long video, I know. The conclusion for this lab, all I want to do is, I found the, what were we looking for? Specific heat of copper to be, in my case, 0.218, don't forget your unit, J, gram, Celsius degree, which is a percent error of 42.6%. And now the reality of it is you should have a total of 4 of these metals to report. Now, if you can figure out a way that makes it less repetitive, please feel free to do that. I would really, Alva Jr., not like to read the same sentence 4 times over. For your source of error, well, that one's going to be on you as usual. I'm not the person who got this 42.6%, but, you know, it could have been you. I'm going to go and throw some ideas, though, at you just for the sake of the video. For some of you, you were very slow on this transfer. Well, what happens is if you're slow on moving this metal over, that metal will start cooling off the second it hits air. So that's why this should have been really quick. Well, there's the source of error. If you splashed any water out of there, well, there's the source of error into there. You know, we could throw several different ideas in here to explain your errors. Oh, here's the biggest one. The reality of it is, and this is the best source of error, and I said I wasn't going to give you a source of error, and look at me. This is an aluminum calorimeter, which means the reality of it is, and we would have done this in physics, you should have done this. You should have had a Q for the piece of metal that you used, a Q for the water. In reality, you should have had plus Q for the aluminum calorimeter. That should, if we would have done this, your percent errors would have probably been much, much smaller. But you would have had to have done MC delta T, MC delta T, MC delta T. You would have had to have got a temperature. You would have had to got a mass of your calorimeter, And if you were in a physics class, we would have done it that way in physics, but in here we just left that off. So anyway, there's you some ideas to help you finish this lab in just 20 minutes and 10 seconds. So, c'est la vie. Bye-bye.